So for all students, you have 3 minutes. We will not use the time question after the presentation. We will go through all the presentation. Then there will be a poster session just after and during the poster session. So most of the students that have the elevator pitch have a poster after. And for those who have no poster, people can also discuss with them after the session.
So hello, everyone. My name is Ahmad Nasser, and I'm a PhD student and part of Link since April. Today, we're going to talk about my topic, model heterogeneity in distributed ML. In distributed learning, as you know, it's like a set of nodes or devices connected through a network, whether centralized or decentralized structure. And we want to collectively train a machine learning model on these devices, across these devices, while maintaining their datasets local and private. Of course, in any realistic scenario, heterogeneities will arise for this case, and this heterogeneity manifests in, for example, differences in the data distribution across the devices. It also manifests in having different models or computational profiles. So devices have different memory, different computational resources, and also different communication channels, for example. So many devices cannot participate in the training or cannot keep up, or sometimes they cannot update the model in time. To solve such issues, there's a necessity to have like heterogeneous models or different models across the devices. This way it would fit their resources. Some of the approaches we categorize and we're working with are related to model subsampling, which is basically a way to shrink the model. So we have one machine learning model here, and we try to come up with many versions of it, like shrunk versions in different ratios. And each client connected to a network, regardless of its structure, is allocated to one model to train, or like shrunk version. And after the training happens, we find a way to collect all of these updated versions and combine them in one way to average the weights. Other approaches we're working with are related to knowledge distillations. We would have multiple models across the network, and after every local training on the clients, we find a way to actually do some type of knowledge distillation between the models so they can share the experiences and the information of the training that's happening. Other approaches also include some type of quantization or pruning. For example, when we have like a model and each model is allocated a subset of layers to train, and aside from these layers, the model can freely drop out or prune the other layers to save space and communication cost. Finally, the objective of this work, the whole thing, is to actually just exploit the computational resources really well of the devices over this network or paradigm. And this way, we actually have more devices participating, and thus we have more data involved in the training. Aside from that, is also to share the knowledge across any decentralized topology, like the decentralized case. And finally, is to actually empower running the trained models on the edge devices, regardless of their computational power. And this is like for inference time after training. Thank you. 10 seconds later.
Hello, everyone. My name is Amal Sakr, a first-year PhD student at Telecoms Paris. I am happy to be here today. I will be explaining an innovative approach of edge deployment and operation through co-investment strategies, where I will explore how coalitional game theory can be applied to ensure efficient and effective collaboration among stakeholders. Firstly, what is edge computing? Edge computing is a technology that processes data near the source. Unlike traditional methods that rely on sending data through the internet to centralized data centers or cloud servers to be computed, processed, or stored, edge computing brings computation near the source. So it can be placed in base stations or access points. This proximity, of course, offers significant benefits in terms of latency and bandwidth network. Why? Because by handling data locally, we avoid the delays with the transmitting data to a distance cloud servers, and by processing data close to the devices, we can reduce the amount of data sent over the internet, and this in turn lowers the cost associated with data transfer. So, but why edge computing is not deployed in today's network? This can be explained by the huge cost associated with the deployment of edge servers at various network locations. So this involves the capital expenditure for running or for acquiring, upgrading, and maintaining physical assets such as edge servers and network equipment. Also, it requires operational expenditure for the ongoing cost associated with running and maintaining these systems, including, for example, energy consumption and network equipment. And the network operator can't support alone this huge cost. However, service providers have an interest in such edge computing services. So we propose a co-investment approach between network operator and service providers to share the cost and the resources between them, and to model the interaction and collaboration between service provider and network operator. We model a coalitional game theory. And we aim to use a dynamic coalitional game to dynamically allocate the resources between service providers. And finally, the problem cost is associated or compounded by the biggest challenge, which is the unpredictability of user demand. So we aim to model the uncertainty by using a stochastic coalitional game. So our model, if you are interested, so our models and results for dynamic and stochastic game are in the poster. And finally, we aim to make edge computing more sustainable by minimizing the energy consumption and taking into account the stochastic energy factors such as availability and prices. Thank you for your attention.
Next one, Ima.
So hello everyone, my PhD is called Analysis of Voting Paradoxes, and I'm supervised by Jérôme Lang, which is a researcher at Dauphine, and François Durand and Elie de Panafieux, who both are researchers at Nokia. So what is concretely analysis of voting paradoxes? So we have people that we call voters, and they have preferences over some alternatives that we call candidates. And we assume that we have an arbitrary distribution over all the possible rankings, and that the voters will pick their ranking according to this probability distribution. And the goal is to compute the probability of some events. One of the events I will show you now is having a Condorcet winner. A Condorcet winner is a candidate that wins all their pairwise comparison. This means that this candidate will be preferred to every other candidate by a majority of people. So if you elect a Condorcet winner, it means that the population will have no incentive to change the issue of the election, because if you change the elected candidate, you will have a majority of people that will not be happy, no matter which candidate you change with. Okay, so how do we compute the probability that there exists a Condorcet winner? We use analytics combined networks. And most specifically, we use what is called the symbolic method. I will illustrate it here on an example. So let's assume that we want to compute the probability that C is a Condorcet winner. Then we will introduce formal variables that will characterize our problem. Here, we don't want A and B to be preferred to C too many times. So we will introduce two variables, XA, that will characterize when A is preferred to C in a ranking, and XB, that will characterize when B is preferred to C. So for example, in the first ranking, both A and B are preferred to C. So we put XA, XB. In the second, only A is preferred. So we associate to this ranking XA, etc., etc. And on the two last ranking, C is on top. So by convention, we put 1. And this gives us a formal polynomial, okay? And this polynomial, in a sense, just represents a voter picking a ranking. And then we do a lot of analysis, a lot of complex analysis, and we obtain results like this. So this is the equivalence of the probability that there exists a Condorcet winner when the number of voters tends to infinity and we have M candidates. So this is a bit complex, but just remember that this is the general idea of my PhD. We have a voting problem. We use the symbolic method to transform this problem into a combinatorics problem. And then we do some complex analysis and we obtain asymptotics. And that's it. Thank you.
Hello everyone, I'm Guillaume Nibert, a PhD student at Snowpack and Sorbonne University. And today I will talk about improving anonymous secure communication on the internet. So first of all, internet is not designed for privacy. If I'm an adversary that put a probe between Alice and Bob, I can see the source, the destination, and the payload of the message. So I can secure easily the communication by using encryption mechanism, but it will only secure the payload part of the IP packet, not the metadata. So in order to remain completely anonymous, we have to use an anonymity network. And there are multiple applications for using anonymity networks, such as avoid being targeted by ads. It is also used to avoid mass surveillance, used by police and intelligence services, and unfortunately for illegal activities. So David Chaum is the inventor of this concept of anonymity networks, and he invented a machine that is called a mix, which takes as an input multiple messages from multiple senders, applies some cryptographic operations, and reorder them in a new order, and relays them to the next stop or the recipients, so that traffic analysis attacks are difficult. There are also Tor-based protocols that are basically a cascade of VPN, random walk, DHT. DHT are core component of anonymity networks, DCNet for sending clear text message anonymously, and also VPN. And they suffer of many kind of attacks, trusted tiers, so corrupt nodes, traffic analysis attack, man-in-the-middle attacks. That's why at Snowpack, we are developing a new kind of anonymity networks where there is no trusted tier at all, both at the network part and at the application layer part. So first of all, a user chooses a set of node and create two paths along this node. Then the route is completed thanks to an auto-discovery mechanism. And in the nominal mode of working, when the user makes a request, for example, to the service here, the IP packet, the metadata of the IP packet are removed. The content is XORed with a one-time pad and it produces a ciphertext. These two elements are sent separately to these two routes. And at the S3 node, they are recombined with using the XOR operation again. The S3 node spoofs the H IP address in the source of the new IP packet. so that the service thinks he's talking to edge. So we are basically separating the upstream flow from the downstream flow, making traffic analysis attacks difficult and also man-in-the-middle attacks. And one of my jobs in my thesis is to know how an adversary can identify a user and how to protect user anonymity. And there are two ways. Either the adversary will use vulnerability flow in the application layer. This is a universal problem. If you want to use JavaScript, you will be vulnerable to JavaScript vulnerabilities. So you have to make some trade-off. We have made a paper on that, especially in the WebRTC API, which is used for VoIP peer-to-peer communication. Or the adversary can directly attack the anonymity protocol. And that's why we have to prove formally the guarantee of anonymity and security. So for that, we use a Tamarin model proverb checker, which is similar of Proverif, if you know. And basically, we have three elements as an input: a model, the specification of the adversary using logic rules, and a specification of properties. And at the end, we have an output of which give a proof that is either falsified or verified for our lemma. Thank you for your attention.
Jorge Mirande.
Hello, everyone. My name is Jorge Mirande. I'm a first-year PhD student under the supervision of Professor Tijani Shahed and Professor Eladina Luyobi. And I'm going to be talking about my PhD thesis, which is the efficient transport of metaverse flows using 5G and 6G mobile networks. Basically, to give an introduction on the general problem, we are going to have two different types of users. One of them is called the metaverse user, who is connected into the metaverse to have a visual and haptic interaction. And just to mention briefly, the metaverse is a virtual entity in which the users are supposed to interact with and within this world with avatars who act as users' alter ego. For these purposes, the visual information will be sent through enhanced mobile broadband or EMBB, and the haptic information at times will be sent over ultra-reliable low-latency communications or URLC. At the same time, we are going to have other type of users called EMBB users who will be accessing to different type of services, as for example, downloading files or shorter in time connections. For the metaverse user in specific, we need to ensure some quality of service or quality of experience in this metaverse environment, to which we will be using the just noticeable difference notion. And this in terms depends on the decoding success probability of the concurrent flows that the metaverse user is receiving. So with all of this, our goal is to optimize the resource allocation, in our case spectrum, in order to comply with the requirements of all the users connected to the network. Here I'm just showing the objective function. We can discuss in detail later in the poster if you want. But basically, our objective is to maximize the transmission rate for the visual information of the metaverse user, and also for the transmission rate of the EMB users weighted by a factor of alpha, while ensuring that the services of all type of users are complied. And so far, what we have reached with this optimization problem is that we have identified in the unfeasible regions in which two of the border of the regions are non-convex. And we also have some steps on the objective function due to the discretization of the available modulation and coding schemes that the user have access to. But we have found a region where we can find the maximum of this objective function. And with this, our plan in the future is to include multiple metaverse users. At the same time, add mobility to both the metaverse and the EMBB users in the network. And later to add a dynamic configuration of arrivals and departures of the different type of users. Thank you very much for your attention.
Next one is Mohamed Amine Legheraba.
So hello everyone, I'm Mohamed Amine Legheraba, and I'm a PhD student at Sorbonne University Leipzig, and my supervisor are Maya Potop and Sébastien Tixey. And today I will talk about an algorithm we have developed, which is called Elevator. So it is Elevator's elevator pitch. I'm working on my PhD on peer-to-peer networks and decentralized machine learning. So I will first speak about peer-to-peer networks. In the literature, there are mainly two kinds of peer-to-peer networks. We have structured networks, where the connection between nodes follows strict rules. And we have unstructured networks, where the connection between nodes are created ad hoc. And if you want to have a dynamic set of pairs in an unstructured network, you need a pair sampling service that will give you, at each period of time, a new set of nodes to connect with. And of course, this pair sampling service can be totally decentralized and only work with the local information. And depending on the way this peer sampling service works, will impact the topology of the network. So in the literature, there is mainly two kinds of topology that appears. The first are random graph topology, where the connection between nodes are randoms. And the second kind, on the distribution of degree in this case, follow normal distributions. And you have also networks based on the idea of scale-free networks, which means that some nodes are more connected than others. And this follows the idea of preferential attachment, where nodes will connect preferentially to nodes that are already connected to a lot of nodes. And this gives you degree distribution that follow power law. And we wanted to leverage on these two concepts to create elevator algorithms. And the idea is that we want a network that will have hubs in the network. That means nodes are connected to all the nodes of the network. So these hubs will facilitate the transmission of information in the network. But at the same time, we still want to maintain some random connection to back up in the case of if the hub fail or crash. So we can still have connectivity in the network, and we can still elevate some new nodes at the rank of hubs, because hubs are emerge organically in this case. And so for the results, we have done simulation on peer simulator, which is a peer-to-peer simulator. We have compared with the algorithm in the literature, and we see that indeed our algorithm is capable of emerging hubs in the network organically, and we maintain all the quality of service and the resilience that we find in the literature. And for the next steps, we will want to formalize, maybe with game theory, how this system works. And we want to implement decentralized machine learning on top of this, because we think that with this kind of topology, we can have better results than the one in the literature like gossip learning and epidemic learning. And you can find the article about Elevator on arXiv. Thanks.
Sanjoy Kumar Jhawar.
Thank you very much. I'm a postdoc at the group of Professor François, and this is a work of large deviation and moderate deviation principle for Poisson navigations. So what do we mean by navigation is, let's say you have a bunch of point process, Poisson points on your plane with, and let's say the point process is homogeneous. And let's say there is a point at the origin, and if you start walking from origin, you always look towards your right and go to your nearest point on your right. Okay, this way you can generate a random graph starting from each point and you always look towards your right and look for the next nearest point. Okay, so this way, in a finite window, you can generate a random graph like that. Okay, so if you restrict yourself in this finite window, then eventually you will meet on the extreme right to just one single point. That way you can generate a tree. So and you can model some traffic network model using this type of random network. Okay, so one key question is to understand, let's say how much traffic is generated on certain part of this window. Let's say can you see the cursor? Okay, so let's say there is a small window here. That means you can see there are lots of paths are converging around that. Okay, so there are lots of traffic generated there. So on the other hand, if you look at this, let's say this part of the window, then there are less traffic here. So you can all the traffic are accumulated along these paths, right? So you can calculate, let's say, some law of large number for this type of accumulation of traffic, or let's say large deviation principle. So to understand some large deviation, that is a measure of how good the network is performing. You first need to understand how these paths behave. So instead of looking at multiple paths, maybe I should say a few things about a very particular model. That is, I just not only look at on the right, but in a cone, in a certain angle, just to use some independence in my model. Okay, so the cone is of certain angle theta. So if you start from just one point at the origin, then you see paths like this, and you can see these paths are deviating, not deviating too much away from the expected behavior, that is the x-axis. Okay, so my goal is to, let's say, quantify, or let's say understand how much it is deviating from the x-axis. Okay, so I denote this random variable by yt, that how much progress you make along y-axis at time t. Okay, and this is one of the result in this project, that is the moderate deviation principle. We also have a partial result about large deviation. Thank you.
Okay, so hello everyone. I will be presenting a work we did with Anna Buzik, my supervisor, and Sean Main about moment-constrained optimal transport for mean-field control applications. So to talk about mean-field control application, an example we considered was this one, where a central planner of a car park wants to charge optimally a huge fleet of electric vehicles. So he must balance two constraints. First, the satisfactions of the EV owner requirements. So basically the vehicles must be charged at the end of the day, and to exploit as much as possible the EV's consumption flexibility, to provide demand size management, or to meet some criteria for the grid. So we will model this problem by an infinity of EVs as a distribution mu of a state variable, where we consider the time of arrival, the level of battery at the arrival, and the starting charging time. So a field interested in transporting such a distribution is, of course, optimal transport, where we want to transport mu1 to mu2 while minimizing some costs. But a difference with control is that in optimal transport, we know mu2, but in control we don't, but we want mu2 to belong to a certain class. So we want to coordinate this agent without the need to know the distribution mu2 beforehand. Secondly, we want to uncut some constraints of the physical behavior of agents. So we want mu to be equal to 0 on some part of the state space. So we add a KAL term to penalize such states. And third, we want to preserve the state distribution for both marginals. Basically, we want pi to be in that set, so to have this form. So we introduced this novel approach, this new problem that we call the moment constraint optimal transport for control, with the three parts I described: the control, the state distribution, and the KL term. To show the application to control, in blue we have the nominal distribution. So the vehicles arrive between 9 and 10:30. So they plug when they arrive. So we have this huge peak. Then we impose as the central planner the constraint in red. So the consumption must be equal to 0.2 between 2 hours. And in green, we have the optimized consumption, which solved the problem and which met the constraint. But the huge peak in green at 12 is a nightmare for electrical engineers. So we also showed that it was possible to implement some slope control. So in blue, we have this slope control, optimize the consumption, which is much smoother. So that's it. Thank you for your attention.
Okay, so it's end of the elevator pitch. Now I propose that we go to the poster session, which is in the outside this room. And I propose also to all the students that presented, but who do not have posters, to stay there and discuss. People may ask them questions for what they present. Now, after the poster session, so I propose to take at least 20 minutes to discuss with some of the students to the posters, and then we go to lunch. So Christina will distribute tickets for that. And for the afternoon, I think we should come back for 1:30 to go on the session on the afternoon. Okay. And thank you for all the students that presented.
I think it's quite a program. Like, if you try to simulate this and like learn something from this, I don't know if you can get this. Like, I don't know. You are generating this much.